All right, so we're going to get started with today's lecture, which is all about fibers in Europe. Most of you will not fall asleep during today's lecture. Not the most interesting topic necessarily, although it lets you do a lot of interesting stuff. But yeah, we're going to power through it. But before we get to those things, I just want to tell you a little bit about where we are in the course. So Gadget 1, the main assignment, not the use case, is going to be assigned on Wednesday. And here's the rough timeline. So Wednesday is assigned. Next Wednesday, you'll have a schematic draft due for Gadget 1. The week after that, you will have the layout draft due, as well as any revisions to your schematic that you have to make. So when we get your schematic, we'll work to get those turned around very quickly. Sorry, did you have a question?
Yeah, we uploaded, when we uploaded the project thing.
The use case?
Yeah, I think I accidentally uploaded to the one that was like S25. So it doesn't show up on the list.
Can you just re-upload it?
Yeah, but is it going to be later anyway?
Well,
We shouldn't hear
I
you.
can tell.
Yeah.
If you tried to upload it, first of all, like last Wednesday, then no, it won't be considered late. Just re-upload it, send an email to see if you get it. Okay, so, yeah, anybody else did that also. So we'll try to get your schematic turned around pretty quickly so that you can make revisions and then do the layout draft. We'll give you feedback on the layout draft, and then the next Monday, that's 5 days after your drafts are due, we need your final files, because that's a hard deadline because we're going to be sending off the boards. We're going to use the week of spring break to have those boards manufactured because it takes time to make the boards. We'll tell you you should order your parts before you leave on spring break so that you have your parts when you get back. And then the week right after spring break will be all about building and testing your gadgets. So that's the plan for Gadget 1. We did, Ross and Brian and I, look at your Gadget 1 use cases last night, and actually most of you came up with great ideas that were actually technically feasible, so good job. Some of you didn't, but we'll be sending feedback regarding how feasible your idea is tonight or tomorrow. So you'll have some time to adjust for your schematic draft. I think when we gave the lecture on power, we sort of overemphasized batteries. And I think every single person said they were using a battery, when really, in at least a few of your situations, just plugging into the wall will make your lives a lot easier. So we'll give that feedback as well. But honestly, yeah, some of you really, if you've got an alarm system that just sits in a corner, probably easier to plug it into the wall. That's always going to be indoors, that kind of thing. Okay. All right. Yes. A question. No, we'll be emailing the feedback. And for many of you, it's just going to be this is feasible. Good job.
Yeah, in a lot of cases, the comments are consider using this sensor for.
So it's going to be separate from the grades. There will be also grading to see how complete your use case was. What we were doing was checking for, is this idea going to work at all, or is it just should redo it or redo this aspect? All right, so some of you may have hit this on assignment 6. This is, I guess the problem is that I've been using an older compiler that if you downloaded WinAVR on Windows, you probably didn't get this file because that's my setup. However, if you downloaded the latest Atmel Studio or CrossPack or Linux AVR JCC, you will probably hit this bug in assignment 6. And basically, the problem is with the delay function that I use in the main program. And the way to fix it is to put this line, pound define underscore underscore, 2 underscores, delay underscore backward underscore compatible, 2 underscores, ahead of pound include util delay in the mg2.h file. So here's mg2.h. Put this line in ahead of it. And I can probably update the files from the website, so if you want to just get a clean copy that's fixed, I'll probably have that up tonight. I have to test it on. Okay. So that's the bug. How are people doing on assignment 6? Has anybody completed it? 2 days early? That's pretty cool. Okay. anybody started it? All right, the rest of you should start it. I know how it is. Okay, so starting with, all right, so now the main part of the lecture. We're going to talk about interrupts, which are really neat ways to get your microcontroller to do various tasks at a set frequency, for example, or to, say, react to a button being pressed immediately without having to go in a loop and constantly check that button. We're going to talk about timers, which are also really good ways to do things at a set frequency, or to create things like pulse width modulated signals, which are great for controlling motors, servos, very cool LEDs that don't actually blind you because you can set them to half power, and also buzzers. So today we're going to talk mostly about using PWM to control motors and buzzers. I don't expect that we'll have time to get to LEDs and servos, but we'll do that on Wednesday, along with sleep, which you all need more. Okay, control flow. So before we get to interrupts, just to give you an idea of how you think of a program. So control flow is a very important idea in computations. You can use it to make jokes. Like, did someone get told? Yes? Oh, snap. No? Tell them. Go back. So basically, inside your microcontroller is this thing called the program counter. It's just counting through instructions. And instructions are things like add one number with another number, or and the way that's usually represented is add this register's contents to this register's contents and put it in this register. Or multiply, although your Tiny doesn't actually have a multiply. You can only add multiple times in a row. Compare A and B. Like when you do like hidden B and underscore BB button or whatever underscore BB PB3, that's just a logical and that's another one of the potential instructions. And then there's conditionals like if C is 0, move the program counter somewhere else. So that's how you make an if statement. So this is actually, fortunately for you guys, we aren't hardcore enough to require you to write assembly code. But if you were writing assembly code, it would look a lot like this. That's at an even lower level than C code. It's just above where the machine is.
So this is what your programs get turned into.
Yeah.
But you don't need to worry about the details of that.
Right. We're just telling you so you have a general idea of how your programs actually execute, I guess. So the way, I guess, another way to think about it is, you read the instruction that's pointed at by the program counter, whether that's add or multiply or whatever you decoded, then you do it, and then you increment the program counter, which points at the next instruction, and then you read the instruction again, and so on. And that's how your program runs. Technically, this is definitely true on like Tiny or any microcontroller. Technically, computers, there's now multiple cores, and they're doing different threads and stuff. So
even in the single core these days, there's micro instruction units. But this is the general concept that they want you to believe, and they make everything so that it looks like this.
And your microcontroller definitely.
And your microcontroller actually does this. Yes.
Okay. All right. So what an interrupt does, so basic example code, like you start in main, you call some sort of init function that's probably setting a bunch of registers, so the program counter is chugging through a bunch of registers. And then you evaluate this statement, while one. So while one evaluates to true, always. And it just says, okay, do this blink function, which probably sets a pin to be an output to on, and then waits for a while, and then sets it to be off, and then waits for a while. And then you go here, and the program counter says, oh, okay, this is a while, so my next instruction should be up here again, which is back to turning the LED on. And you never actually reach here. If you're familiar with programming in general, you know that infinite loops are bad, but with microcontroller programming, infinite loops are good because there's no operating system So you have to have an
program.
increment.
Yeah, if you exit your program, basically nothing useful happens. It just reads right off the end of your program and starts executing random stuff at the end of memory.
So if you have like a small program that you program over top of a bigger program, it can actually go into the bigger program.
It'll just read right off the end. Like think of if you cut out a small piece of paper and pasted it on top of a bigger piece. It'll just read right off into whatever you're doing.
So you always want to have an infinite, basically. Here's another example. So you've got a sentence, you have your nit, your sentence is being read, like you're reading a register that reads presumably an analog input, and then you're doing a condition, so it's a branching. So the program counter says, okay, I'm going to evaluate this statement, sentence is greater than 100, and if it is, then I'm going to branch to here, and if it's not, I'm going to set the program counter to branch to this expression. Okay, but here's something a little more mysterious. And this is, again, this is the use of interrupts. And I'm just using analog interrupts because you're somewhat familiar now with the analog system and what's happening. So we have declared way up at the top a global variable, which means that this variable can be accessed in main and also in other functions. And it has an interesting keyword in front of it called volatile, which I'll talk about in a minute. But just notice that it's there. So you have a main, you do an initialization, and then while one, if sense is greater than 100, set the LED, otherwise set the LED to off. Now, the interesting thing about this is we've never set sense to anything. We didn't say sense equals read analog. So what's happening is there's this special function here, which is an interrupt service routine. And it fires every time the analog subsystem says, I've completed a conversion, there's a new value in my register. So you can think of this as happening asynchronously from this. So this is just getting fired whenever the analog function says, hey, I've got a new value. So when that happens, you say you set sense to the analog value, and it gets updated. And so if sense is greater than 100 one time, you set the LED, otherwise you set it off. So it's just, in theory, it does exactly the same thing as this. But it does it well, yeah. All right, not in theory, I should say practically, when you see the result, it does the same thing. But it does it in a completely different way. It uses an interrupt. And there are many situations where the only reasonable way to do things is to use an interrupt. Okay, so interrupts are a way to interrupt the controlled flow. To go, instead of having the program counter just go chug, 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 suddenly the program counter goes over here because it's thrown an interrupt. So yeah, obviously engineers love obvious names, so interrupt is, it interrupts. So it allows certain events to alter the control flow, which can simplify your programming a lot. So, and there are, if you look even at the AT-Tiny data sheet, and you look at all the sources of interrupts, there are probably 30 or 40 of them. So there's lots of different things that can throw an interrupt. So it can simplify some types of programming. You don't have to constantly check for values, just polling, which is oftentimes can be a very inefficient way to do things because you've only got a single process. And you can configure it to handle things like, analog conversions on button press. There's new data on my serial port, gadgets on fire, stuff like that.
Ambient temperature, that is actually a real thing you can interrupt on.
Yeah. There is a little tiny temperature sensor inside your Tiny, and it's not very good, which is why we haven't really talked about it, but it basically tells you if it's on fire or not on fire. And if you okay, so comparing these two programs, well, we've already sort of talked about it, but notice what happens here. Like, in this program, we have a loop and a delay of 1 second. So what this is doing is it only reads the sense value once a second. In this case, we have an interrupt, which just sets the LED, and the main function just goes to sleep. So basically, this doesn't react more than at a rate of more than once per second to new sensor values.
And in fact, it is at a rate of roughly
Yeah.
1 second. So if something changes halfway through that second, nothing's going to happen. Whereas on the left, we're doing this basically every time this interrupt service routine fires. So it doesn't matter how many sleep cycles happen. If that interrupt triggers, which is new ADC read, we'll immediately run this piece of code, which updates the sensor value.
Okay, so some other simple uses, like, you know, this PCInt stands for pin change interrupt. So basically it says if a pin on one of my ports changed its value from a logical 1 to a logical 0 or vice versa, throw an interrupt. You can check which pin it was. If it's a certain pin, maybe you hit like the E-stop on your robot. So you probably want to deal with that right away. And then also, like, you can check the motor temperature. Maybe you've got a motor with a temperature probe on it. If it's greater than a certain value, turn off your motor right away. So usually with microcontrollers, there are certain things, especially when you get bigger embedded systems, that you want to do right away. That's one case where interrupts are good. All right, so how do you use interrupts? Typically, it's just another bit of register configuration. So when it comes to, for example, like we're going to show you how to use them with timers, but with the analog, if you want to use an interrupt, you just configure your analog device as usual, and then add this magic, which is ADIE, which I think is the analog to digital converter interrupt enable.
Yep.
So you basically say, please enable this interrupt. The other thing you should note is that if you want the analog to run all the time, you can set it in a certain mode, free running mode, where it's just constantly converting, constantly reading. So it'll be reading that interrupt or hitting that interrupt a lot. You could have a sleep routine that just turns it on every certain number of milliseconds or whatever. And you can do a few other things with like pre-scaling it and setting how often it reads using the clock so that it isn't constantly reading very well. But that's not all. We need to do a little bit more. So you saw the ISR function, so you need to define one of those. If you enable an interrupt and you don't have an ISR interrupt service routine that matches that interrupt, and it matches it based on these wonderful codes that are defined in some obscure document that you should have a link to, but which we'll definitely link for the next assignment where you're actually going to need interrupts. If you don't have one of those, basically your tiny, like, it throws an interrupt, but it's not serviced. And what happens if it's not serviced is it goes to a default vector. It like sets it to all zeros. That default vector is a reset vector, which just resets your program. So not creating an ISR basically you get this situation where you turn on your mini gadget and it's just constantly resetting. Not a good thing.
So basically, by default, the reset vector is for your main function, which is usually not quite what you wanted.
Right. And then the other thing you need to do is there's a default function called SEI, I think set enable interrupts. I may just be making that up, but it enables local interrupts because your Tiny won't throw any interrupts unless you've enabled interrupts globally. So basically, you need to separately set, usually at the beginning of your program in like the init function, that interrupts are on. And then you can use CLI, which is just clear interrupts, if you want to turn interrupts off. You don't want any interrupts. You can do that briefly if you need to disable them for something. Now interrupts come with danger, errors. So I already talked about that. If you forget to define your ISR, that's just going to censor a reset vector. You may need to make a volatile variable. I think we have an example in a minute There's all sorts of other stuff. Race conditions where your like interrupts are triggering too quickly. You could have an interrupt that runs so often that the rest, if you're trying to do something in that main program, it just doesn't do it because it never gets to it. It interrupts too often, and every interrupt routine takes too long to run. Like if you have a routine that takes 5 microseconds, but if you're interrupting every 1 microsecond, you're just blowing up, like nothing is gonna happen.
Yeah. So basically, all of these boil down to an interrupt can happen at any time, basically immediately. So it's like, oh, you're in the middle of setting this variable, well, screw you, I'm gonna go and like do this other bit of code, right? And that can cause a lot of problems if you're not thinking a little bit about how your code works in your main function or wherever. And when you use multiple interrupts, then you
Yes, so next. Now there's one caveat to what Cross just said. An interrupt cannot happen when you're dealing with another interrupt. So, you know, like you could miss an interrupt, or usually what happens is they queue. Like you have an interrupt and then the next one happens right after that, but it may not be perfectly timed if you want it. So interrupts are automatically disabled when you're in another interrupt. More advanced microcontrollers, I mean, you guys are really using like for 2012, the simplest microcontrollers around, essentially. They've still got a lot of bells and whistles considering, but like more advanced microcontrollers have like interrupt priority, so you could say this interrupt is more important than this one, deal with it. Even if you're inside this one, deal with this one. Like that's good for like your emergency stuff. You know, you want that stuff to be highest priority, on fire, that kind of thing. But the timing doesn't happen, so you just.
So in general, the easiest way to make sure that you minimize the problems that you have with interrupts is to reduce the amount of stuff that you're doing in interrupts. What you want to do is keep it really, really simple. You want to just set a value or change little things that don't take a lot of time to do. You don't want your interrupts to go and like run a whole signal processing algorithm for like an hour or something. That's going to cause problems. You want to do something like set a variable with a value, or flip a bit so you turn on an LED or something like that. And keep in mind that you can usually set some sort of variable which then will tell your main code to go do something which will take a long time later. And that's usually what you want because of this problem of if an interrupt's running, it's usually screwing up other stuff that could be running at that time.
So the most you would put in an interrupt is like 3 or 4 if statements.
Yeah.
Because those are evaluated pretty quickly.
And to give you an
Avoid
idea,
that,
Yeah.
set a few torts.
so to give you some idea, like even something like a printf, which it's like seems innocuous. Oh, when the ADC triggers, let me just print out, oh, here's the value of the ADC. This will cause major problems. Don't do this, because the printf actually has to convert a bunch of characters and then write them out to the serial stream. It doesn't terminate until every byte's been written, and that entire time, your main function is on hold, like none of your other interrupts are getting called, like it's just bad news. What you can do is set that value to a variable, and then in your main function, just print out the value of that variable, and that'll work fine. But yes, this is not just true for microcontrollers. This is also true in general for coding with event-based systems. If any of you go on to do that, the same caveats apply.
Okay.
Yeah.
Sorry, I didn't understand the punishment in terms of utility knows everything else from why would anything happen?
Well, the issue is that you don't know when these things are on hold, and you don't know if something else wants to interrupt as well. So think about if you had, say, 2 timers running, and you wanted one to trigger when, you know, every 100 hertz, and you want another trigger every 200 hertz. But the 100 hertz function takes like a second to compute, right? Basically what's going to happen is that first one's going to hit, your main function's not running, the interrupt's not going to get called again because it's already being serviced, your other timer's not going to get called again because this one's being serviced. And so now all of those have been delayed, right? And so that can cause issues. So that's the sort of thing we're talking about, is that if these things take too long, then basically other stuff which was supposed to be happening at regular intervals that you expected to happen could be delayed.
So the way you prevent things from, you know, getting out of sync, essentially, not happening at regular intervals if you want them to be at regular intervals, is to just make sure the interrupts are as short as possible. The code inside the interrupt, have it do as little as possible. Yeah. Okay, so some examples of like ways in which the compiler can screw you up.
So this is the volatile.
Yeah, this is where you need like volatile. So, you know, you've got your interrupt service routine. It's reading the ADC register value into this sense variable, which is global. And what this function will do, or what this program will do, is the LED is just always off. Because up here, in the global, like in sense, when you declare that, it sets it sort of automatically to 0. And it then goes immediately into this function, into the main function. And in here, it's just considered 0 because of the way the compiler optimizes it. The compiler doesn't realize that sense can also be updated in the interrupt unless you tell it that. And you do that by saying it's a volatile int, which means it can be changed asynchronously at any time. So that's why in the previous examples we were using volatile in sense.
Yeah. So essentially, when compilers are taking your code in, they do all sorts of optimization because there are a lot of inefficient things that you're doing that you don't even realize that, you know, basically certain things can be compiled to very, very simple register instructions and stuff like that. So if you don't flag stuff like this, for example, volatile specifically says this is a piece of memory that could be changed from anywhere at any time. So don't make any optimizations that assume it hasn't changed just because I haven't touched it in one place. So if you don't report stuff like that to the compiler, it can optimize out things because it thinks it's being smart. It's thinking, well, I just saved you like 1 billion cycles because now you don't have to do this while loop at all. Like I've totally solved this problem, you're good to go. And then in reality, what it's done is just completely works what you were trying to do. And so basically, it's just a matter of telling the compiler what you actually want. And the volatile keyword, in this particular case, is telling the compiler, what I want is for this variable to possibly change from multiple places. So treat it as something which is volatile, which is you're not sure about.
Change. Don't be so sure that it will not change.
Exactly.
Okay, so another one. So here, you know, maybe you're counting something up at a certain frequency. Let's say it's 1,000 times a second. So maybe 1 second you're saying if the count is equal to 1,000, set the count back to 0, do something amazing, otherwise do something boring. The problem with this is that at 1 second you may or may not do something amazing or boring. And the reason is because you're using a double equals, you're assuming that count is not going to somehow skip from 999 to 1001. Because, you know, what could happen is in your statement, basically, you know, count is 999, or let's say count is 1,000 right before you hit this if statement, but that's when your interrupt fires, and it increments it to 1001, and then you get to your if statement, and now count is 1001, so it's not equal, so you're screwed. And considering that this, you know, runs probably once a second, eventually this will happen. It may not happen the first time, the second time, or the 50th time, but the 51st, you're like, hey, how come it's no longer doing anything amazing? And it will not ever do anything amazing ever. Well, till it opens.
Yeah.
So how do you fix that opposite?
Well, it's actually really easy in this
Greater
case.
than.
Just change this to a greater than or equals to, and
Yeah.
that should catch. Because it's unlikely that you'll skip like 1,000 counts, and that's how much you have for your overflow. So
But like taking out volatile would not.
taking out volatile will do something else, which is not
You would just
amazing,
make
which
count 0
will
forever.
basically treat this as count 0 forever. Yeah, that's right.
So yeah, you just use a greater than. You sort of have to anticipate that your number, the number that you're using, may just skip a little bit more than you expect. Okay, so time to get to timers. Time for timers. So timers are a way to generate interrupts with a certain period. Like you want it to happen, you know, once every millisecond or whatever. And you want this function to trigger exactly then. They also have a few other characteristics to talk about. The AT Tiny has, oh, sorry, you have a question?
Yeah, in the previous thing, if it was something like 2 milliseconds instead, how would you?
If your timer was counting at like
Yeah.
1 millisecond,
Like instead of 1 second, if it was like 2 milliseconds.
I mean, everything should work pretty much the same.
Yeah.
Right, so basically, this is just something, like 1 second would just be some number, like 1,000, because this is counting up at every millisecond. So in this case, it would change from 1,000 to 2. Right. So, but the rest of the code should be pretty much the same.
It matters a little bit how long it takes to do something amazing. Because if it takes longer than 2 milliseconds, you may have this case where it's like, let me think about that.
Well, it would just skip one and then do it.
Yeah.
Yeah, it may skip it.
Yeah, which can happen. Basically, this is just executing however fast it executes, and this is just happily taking it up again, right? So then when you get back there, depending on how long this took, you could have counted up by however much. But if you have greater than or equals to, then you'll just trigger again, right? So it may not be at 2 milliseconds if your thing takes longer than 2 milliseconds
Right.
to do something amazing. But it'll still work. Whereas if you did equals, it might just never
But it
happen because after the first time, you just start counting up forever.
But if do something amazing took more than 2 milliseconds, then instead of triggering every 2 milliseconds, it would be triggering however long it took. Basically, you'd just constantly be doing it, I think is the result of that.
Yeah,
At
at whatever speed.
at however long it took to do something amazing. So yeah, that is a case where it would be almost useless. You really, for this to be useful, you want to do something amazing to be significantly less time than the time you want to count for, I guess, for it to be interesting and actually periodic in a way that you control. Okay, so yeah, so the ATtiny has an 8-bit timer and a 16-bit timer, so multiple options, which is great, actually. It's great that you have a 16-bit timer. If you don't know how great that is, it makes some of your work a lot easier.
The 8-bit timer can only count up to 256. So for the many applications in which you want to count to something higher than 256, the 16-bit timer is your friend. So,
So if you think of a counter, what a counter does is it has a number. It counts it. It counts up by 1 or down by 1. You can choose which way it goes. And how often it does that is clocked either by your system clock, which on your Tinys is currently running at 8 megahertz, roughly. It's not perfect. It's probably off by up to 10%. Or you could clock it with an external input. So you can get a second clock or something, and you can say, every time this thing goes high, count up by 1.
or every time this button gets pressed or things of this
Yeah,
nature.
so you can count button presses, for example. You can tie it to some hardware built into your ATtiny to make PWM signals.
This is exciting.
That's weird. I thought it was somebody's cell phone had a really realistic sound. So yeah, you can generate pulse width modulated signals.
Oh, sorry, yes, this is the front thing. That was totally the wrong number.
They're looking for.
They were looking for IT. Anyway.
Okay, so you can also use it to generate software PWM, which is basically a signal that occurs at a certain period. Since your counter, can create interrupts that trigger at a certain period, that's the way to do it. The bottom line is that pretty much all of your gadgets as proposed, most of you propose some form of LED display. Probably you don't want them to just turn on and off, so you're going to need software PWM for that. If you have a buzzer, you'll need hardware PWM. If you have a motor, you'll need hardware PWM. If you have a servo, you'll need software PWM. And we're going to tell you how to do that in the next 2 lectures. So you'll need this in order to make your gadgets work, as well as for Wednesday's assignment. Okay, so here's the block diagram of the 8-bit timer, which is somewhat simpler than the 16-bit timer, which is why I'm focusing on. So let's see, let's go through this. Okay, so there are 3 registers that are kind of important. There's the timer counter register, which I think that one holds, let's see, yeah, so that one just holds the value of the counter. So, an 8-bit register, it can hold a value between 0 and 255.
So this is the part that's doing the counting up or counting down, right? That's the actual timer or counter.
And then there are these two output compare registers, which you can compare against the value of the counter. And if they match, you can throw an interrupt based on that.
So this thing is counting, and then these guys are basically what you set to be the important values of the timer counter where you want to do something. So for example, say you had a timer and you wanted to have that timer halfway through that timer you wanted to flip a bit so that you turn your LED on and off at the time. So you can set one of these to be at a low value, one of these at a high value, and then that way you can set your LED on at a certain time and then off at a certain time. But they're both just compared to that one timer that's just going up between 0 to 256 and then looping around or whatever.
Yeah. So yeah, and you'll notice they all have like these little ends. That's just the way that the AtMel data sheets refer to different ones. Like if n is 0, if you have TCNT 0, that refers to your timer counter 0 module. You have two. You have a timer counter 0 and a timer counter 1. So
This is basically just their way
I
of
know it's-
not having to put two diagrams in for two completely identical timers,
if they had to.
if they have to. The bigger chips can have like 3 or 4 identical
same.
timers, and so they just use this.
Because they're just so useful. But yeah, so it's a lot of alphabet soup. It's really kind of hard to remember the acronyms, but basically that's what those two do. And then there's the timer counter registers, which I'm trying to remember now.
They set what this thing gets set or reset to, depending
Yeah.
on stuff. So basically, what these things do are, depending on the mode of the timer, these set what T count will be on
Next
certain
time
events.
around.
So for example, if you're counting down, when you get to 0, I want to load it back up with the values in this register. Or when I reach 256 now, I want to start from, not from 0, but from 20 or something. And so that lets you adjust the timing and so forth, things that you're doing.
Okay, and then you've got these interrupts. So, this one, for example, is being thrown whenever the timer counter is the same, it's equal to the output compare B. It'll throw the output compare B interrupt. Same with output compare A. And then there's the TOVN, which is the timer overflow interrupt. And that happens whenever your timer hits top, which is actually defined by you. It's a register configuration thing, but you can define it as either the maximum value, which is 255, 0xFF, or you can define it to, actually, I think you can define it to one of these. So you can say, actually, I want my, the top value that you can count to be 100, which I've loaded into output compare register. And so that can throw in interrupts as well. And then you have a couple of ways to tie these into actual hardware pins. So there's the output compare A and output compare B pins that are associated with this timer counter module. And you see this like waveform generation. That's how you make hardware PWM, hardware pulse width modulated signals. And then there's also the TN, which is just an input source. I was saying you can have an external input to just count up or count down like your timer. So every time you hit that pin, it will count your timer by 1.
So basically, this giant block diagram is just because there's lots of different ways of configuring the timer to count up and count down and throw events when different things happen. And basically, there are many different ways, but really we're going to use probably 2 or 3 of them that you'll see for things like servos and pulse width modulation. And yeah, the difference between hardware PWM and software PWM is really just if you have this directly connected to one of these pins, you just don't have to touch it, right? It's just doing its thing, it's producing some waveform, it's driving your motors, and you never look at it again. If you have it going to one of these ISRs, these input service routines that you wrote, now every time this thing goes off, you're doing something, and so you have to keep track of what you're doing. So that's the software part, is it takes some time in your code for you to say, oh, turn this bit on and load a value or something, versus not having to do anything and care about it at all.
All right, so timer interrupts. So like I said, there's the timer overflow interrupt, which is just whenever your timer overflows. When people talk about overflow, what they're typically talking about is let's say you've got 8 bits and you're counting up, you count from 0 to 1 to 2. Eventually you get to 255. When you count again, it actually overflows and wraps around and goes back to 0. It's essentially the way it works. Like that's just a hardware active life. So you just interrupt whenever that happens. And like I said, you can set that value to not be 255. You can set it to be something else. And then there's the output compare interrupts. So there's multiple of those per, I shouldn't say per interrupt, I should say per timer module. So you usually have 2 on the tiny, on some other ones you can have like 4 or even 6. And you want to set the output compare to some number, like you might set it to 50, and then whenever the timer hits that number, it's going to throw an interrupt that you can use for either pulse width modulation generation, or you can make some sort of software routine around it. Now note, unlike with timer overflow, when it hits that interrupt, the timer counter just keeps counting up. Like it doesn't go back to 0 or any other number, unless in the interrupt service routine, you actually directly change it. So the timer counter register, like that's just counting up all the time, you can actually set that to some value at any given point, whenever you want as well. You don't have to like just let it keep counting. Okay, so where are these magic pins that can do all sorts of stuff? So here's your AT Tiny. It has 14 pins. And if you look like at a certain part of the data sheet, you see some of the other functions of each pin, and it's sort of encoded into acronyms, but if you look closely, like on pin B2, you have OC0A, that's output compare 0, so your timer module 0, I guess the A output, and then you also have output compare 0B. And then on pin A6 and pin A5, you have output compare 1. That's the 16-bit timer, so you can generate high resolution PWM signal off of that. And then you also have T0 and T1. Those are the input signals if you want your timer, if you want your counter to count on some external pulse, like a button or something, you would hook the button up to T0 in order to make the counter 0 increment whenever you touch a button. So that's where they are. So this is actually important because if you think about, like, let's say you wanted to control a motor in your mini gadget or a buzzer, you would have to put the motor control pins, the pulse width modulation pins, or the buzzer pin on one of these. You couldn't just pick any random pin because this is where like the hardware allows you to make very high frequency pulse width modulated signals, which
So now,
you need for a buzzer.
one thing which comes into play when you're making a really fancy gadget with lots of stuff is you can see that this same pin is doing a lot of stuff. It's got an interrupt, it's running the timer, it's doing some serial stuff, it's also an ADC, it's analog to digital input. Now the problem happens that in these microcontrollers where each pin's doing like 12 different things, you have to be careful that you're not actually planning on using 2 different functions that both use the same pin. So if I wanted to read my 6th ADC value and I also wanted to use the output compare of this timer, I couldn't do that because they're both outputting on the same physical pin. And in most of these microcontrollers, each of these pins is carrying 5 or 6 different functions. So when you're designing your gadget, you have to keep that in mind, that the actual physical pins on your device might be a lot less than the functions that are available on your device. You might have 8 ADC channels, but 3 of those channels are also being used by something else that you need for some other function.
Yeah. You switch.
Well, you can switch which module is active. Yeah, you can do that at runtime, but you have to sort of deal with the circuitry problem of you still have the thing physically connected to whatever.
I need like a multiplexer or something.
Yes, but you can do that, and that is one solution to this problem. Yeah.
Although if you've got like a PWM signal, for example, usually that has to be on at all times. Otherwise, you have like a maximum 50% duty cycle or something.
Yeah, these output compare pins can.
So the ones in green,
yes. Keep in mind that they're tied to a particular timer. So if you're doing PWM on 1, right, that means that your OC1B is basically also stuck with that same timer at whatever frequency.
so you can still use the pin normally.
You can use the pin normally, but you couldn't have a different PWM running.
So this
Well, there's two PWM sources. So basically, like, you have two timers, and each of those can generate two PWMs at the same frequency.
Yes, exactly. So you're tied to the amount, the frequency. So you couldn't make OC1A run at 5 kilohertz and OC1B run at 20 kilohertz.
Yeah.
They both have to run.
Because
at
they're both
5.
on the same block, that's counting up at the same rate.
So
So
this
they
is-
can have different values.
So this is important if you've got like a buzzer where you actually want to modify the frequency over time because you want like a high note and then a low note. You wouldn't use OC1B for the buzzer and OC1A for motor controls because you don't want to have a variable frequency going into a motor that would cause all sorts of problems.
But you can use both of those channels for two different motors, that'd probably be complicated.
Yeah. Okay, so let's talk a little bit about the clock sources in a little more detail. So your clock, you're running it at 8 megahertz. If you want to use the system clock, you can, and you can even use something called a prescaler, which basically divides down your clock by a certain number. And that number, on the timing UR options are 864, 256, and 1024. Now keep in mind, that's if you want to have like a periodic interrupt, like let's say you've got just the most basic timer overflow, so it interrupts every time your timer gets, or your counter gets 255, right? So that's going to happen, you know, so let's say your clock's 8 megahertz, you divide it by 8, so now you're at 1 megahertz. That's how fast you're counting. So you're counting 1, 2, 3, 4, 5 at 1 megahertz. You're going to overflow, you know, every 256 count. So your interrupt's actually running at like 31 kilohertz. Yeah. So you have to keep that in mind. Like how fast you interrupt is not the same as how fast you run your clock. So your clock I/O, you can use clock I/O, or you can use this external clock or some sort of other external source. It doesn't have to be a clock. It can be a button that you press
Yeah.
however often you know.
It doesn't have to be at a fixed frequency either. Basically, this is just any time it sees a certain type of transition which you specify, that counts as a clock. It's one clock.
And so you can set this, you know, this is again more register selections. Like how you set this is just a bunch of, or setting a bunch of bits in registers. Okay, so timer counting, you know, you can choose what happens here. So the timer can go up, timer or the counter can go down, or it can clear every clock cycle, whatever it does. What it does depends entirely on how you set the registers. There's also these waveform generation modes.
Basically, each of these modes is a different way of the timer being counted and being reset.
Yeah.
So you can see that basically these three columns are telling you basically what we're counting up to. What happens when, I think this is when we hit an output compare, or is this?
Yeah.
when we-
No, it's when the output compare register gets up.
Okay, so when the register gets updated and when our overflow hits. So for example, in normal counting mode, we count all the way up to 0xFF. That is the biggest value we can go.
250.
Right. We'll immediately update this register, and we'll overflow when we reach max, which is also 0xFF. So basically, this is just count all the way up to the maximum, throw an overflow interrupt when that happens. In PWM phase correct, this is a mode that motors sometimes like. Basically, instead of just counting all the way up and then overflowing, it counts all the way up, and then at the top, it switches direction and counts all the way down again. And so here, you're counting up to 0xFF, but the overflow flag is set at bottom at 0 because you have to wait until you've counted back down again.
So your interrupts happen every 2
Yeah.
cycles essentially.
Yeah, so this is like a special mode that is essentially used for motors so that they have a more balanced input when you're using multiple phases for that sort of thing. And then we have fast PWM, which is very similar to normal, except I think the clock
just
is
counts
twice
up.
as fast.
Well, it just counts up.
It just counts up and then
goes back to
Yep,
0.
but I think it does it twice as fast as you can do otherwise. And then you have other variants of phase correct.
Yeah,
other
so
variants.
notice the difference here, the phase correct and the fast PWM here. You're counting, instead of counting all the way to the top, you're counting to output compare register A,
Right.
which you can set to whatever.
So
You
you
can
count
even
it.
set this to 1.
Yeah.
You know, you can start at 0, count to 1, overflow, done. If you want to run stuff really, really fast. I don't advise it because probably you can't handle running it effectively, but,
Yeah, so there's all these
Sure.
modes, you probably don't need most of them.
yeah.
We'll
talk a
We
little
will talk a bit more, but basically these top few are probably what you're gonna want.
Right. So we'll talk about these in some detail. So yeah, we talked about normal mode, you just count up, you overflow, you set your interrupt. Yeah, and then there's like random text that in the data sheet, if you go into detail, like the output compare unit can be used to generate interrupts at some given time. What they're basically saying is, you set it, you set your output compare to a certain value, you can interrupt, every so often. They suggest that you don't use this to generate waveforms, like waveforms for driving LEDs, pulse width modulated waveforms, because they have these cool hardware units. But let's say you've got like an RGB LED with 3 outputs, and you want to control them individually. They don't give you enough hardware to really do that with one timer module. So one way to do that is to use software. And so we're going to talk about that in detail Wednesday. But you can use software if your routines don't have to happen that often. If we're talking about like something that happens at 100 hertz or 200 hertz as opposed to 20 kilohertz. If you're doing anything at 20 kilohertz, you pretty much have to rely on hardware. So yeah, that's basically what that statement is saying. So for LEDs and servos, you will be using normal mode in order to do this, and then supplementing it with software service routines. Hello. Computer.
Oh, there we go.
That was weird. And actually, it's still not actually reacting, but we've got the next
Oh,
tab.
now we got another one. Let's go back.
What is going on?
Okay, everything is
All right.
cool, just let it be.
Computer went. Okay, so fast PWM mode is the one that you're most likely to use if you've got a motor or a buzzer. So like we said, it counts until it reaches the top, and you can set that as either the maximum value or output compare register A if you don't want to use the maximum value. And you can set the pins, the hardware pins, to toggle whenever the counter reaches that output compare register value. Well, whenever it reaches output compare register A or output compare register B. So that's how you do hardware PWM. So if you think about, okay, let's talk about that first. You can also set the pins to toggle and be at a 50% duty cycle, so you're not controlling the duty cycle at all, but you can change the frequency easily. And that lets you run a buzzer, because a buzzer, you just give it a square wave that's on 50% of the time and off 50% of the time. And how fast that's running is the tone that will come out. So if it's at 500 hertz, you'll hear a 500 hertz tone, which is roughly the frequency of people's voices. If you want like something that will irritate children and not adults, you give it a 15 kilohertz tone, which you won't hear if you're over 25. So yeah.
I think this next slide has this graph, which makes it too helpful. Just keep pushing buttons. And these Electron CPUs.
Okay, so
Do you have to touch the screen again? Is that it? Oh, there we go. Okay, so this is a diagram that is in the data sheet, which if you don't understand what a timer counter is doing, looks very scary at first. But actually all it's doing is telling you what's going on with each of the individual bits of the timer counter as it's running. So this period at the bottom is just so that you can this is one period of the timer going on. And here we have our timer, and you can see it counts up until it reaches top, and then resets, and then it counts up until it reaches top, and it resets. And that's all it's doing. It doesn't really give a crap about what's going on in the world. So now we have our output compare pin, right? And so this is tied to the value that we set in some output compare register. And so we set that to some intermediate value, so that's what this line designates.
70% of time.
Yeah, and so basically what's happening is, okay, so we didn't, here it wasn't set, here it wasn't set, here we set it to something. And so now what happens is, here after we set it to some value, when we count up to this value, all of a sudden this goes low. This output compare goes low. And then we finish counting and it gets reset. And then we start counting, we reach the value, and then it goes up. And then we finish counting and it gets reset. And you can see that as we're doing this, we can actually change the value, and that varies how long it's low for the same fixed period. So this part hasn't changed, right? But these lengths have, depending on the value. And so that's how we're going to control stuff like motors and LEDs. If we have them off or on longer, then basically they'll look brighter or they'll turn more powerfully because they're on more of the time. So that's how we can use duty cycles with these timers to control those devices.
And so this is, I mean, this, if you're controlling motor, this is happening at like 20 kilohertz. So it's happening so fast that you're, like this period is happening in, I guess, 50 microseconds. So it's happening so fast that the motor essentially just sees it as an amount of power being chucked into it. It doesn't really notice that it's turning on and off that quickly. With an LED, we do it at about 100 hertz or 120 hertz because your eyes just can't detect anything that moves faster than 160 hertz. So like those fluorescent bulbs are all going at 60 hertz, but we just don't know. Most of them. And so notice also, I guess, minor detail, you can set the register to make it so that the output is either regular or it's inverted.
Depending
And
on
that's
what you
just,
want to do.
that's just another register setting. You can say, okay, I want it to go low until, you know, I hit my output compare register and then go high, or vice versa.
All right, click things. I think it's
Now
just
that,
that.
that's independent, yeah.
Yeah, wow, it's really glacial. Oh. The mouse just disappeared. It's very strange. Does anyone know anything about using PowerPoint in Windows XP? Probably PowerPoint for 5 years or something.
Does anyone want to donate a computer real fast?
So you can use it online and do it. And it's Linux.
This is why every one.
Okay, here we go. Good,
Yeah,
good,
all
good,
right.
good. Okay,
Okay.
so now we have 2 new exciting
I'm
things.
just gonna hit the button all the time.
Oh, God. All right, so we have like 1 second to figure out this. Okay, so CTC mode is, well,
It's basically obsolete, but you could use it like, all right, so CTC mode is basically obsolete. You can use it like the fast PWM mode in order to make a buzzer that goes at a set, or that goes at a variable frequency at a 50% duty cycle. So for example, just looking at the chart, you notice the period is changing, but the signal is on 50% of the time each time.
yeah. So basically your timer counter is not counting up to the same value.
Yeah.
That's the big difference.
And that's what happens in a certain way of setting fast PWM.
And this is what I talked about before, phase correct mode, basically your timer counts up and then down, then up and then down. And that whole down-up cycle is one period. And so basically the advantage of this is that you can trigger sort of halfway through on your up count and then trigger again halfway through your down count. And it sort of centers your wave, so it's always in the middle of that up and down count. And so when you're driving motors, that can be useful because it means all of your phases will be centered. So if you're turning on 2 different phases of motor, you know that they basically have the same centered waveform. There's not one that's starting earlier than the other because it was on more.
So it can be useful, more useful with high-end motors. Like
Yeah, you guys.
fast PWM is probably fine for the motors that you'll be driving.
Anyway, fancy modes, wonderful.
Yeah, okay. So hardware PWM, to summarize, you don't need to create, well, it requires interrupts in a sense that you don't need to create
Interrupt
interrupt
service
service routines and handle it in software. How you configure your registers is the key element. So register configuration for timer 0 is section 11.9. 12.11 is register configuration for timer 1, and 13.3 talks about the prescalers. So that's, the prescaler is, again, how much you want to divide your clock frequency by. So you need to set bits in these registers. These are the timer counter configuration registers. There's typically 2. And then you may also need to set the timer counter value, the output compare register value, and so on, to make the hardware PWM go. But in general, it's a little bit easier than software PWM.
What are those sections from?
The data sheet.
Oh.
So the AT Tiny data sheet. And is that? Okay. There's still more. Yes. So, so just to talk about how you configure things a little bit, go into a little more detail. Like, here's an example. What we want is we want to set the fast PWM mode. We want it to count up to its maximum values of 255. And so we're going to go through everything you need to set in order to make that happen. But this, just as a note, these instructions work on timer 0. Timer 1 is a little bit different because it's 16 bits, so you'll have to do a little bit of reading to actually convert this into timer 1 instructions. So first of all, there are 3 bits which are part, I think, of the timer counter configuration register B. It could be A, though, I could be wrong. There's only 2, so you'll figure it out in the data sheet pretty quickly. And how you set those bits is what kind of mode of operation you get. So we want fast PWM that counts to 255. So we would set those bits to those values. Simple enough? Hey. Okay. We want the output to actually appear on the hardware pin because we want it to actually create a real signal that we can use to interface with motors. So in order to do that, we don't want normal port information because then our output's disconnected. We don't want whatever reserve is. So what we want to do is we want to clear the output compare register on the match and set it at the bottom. So what that means is, like you were just looking at the fast PWM timing chart, when we're at 0, we set that pin high. When we get to our output compare register match, we set it low. Then we count all the way to the top, we set it high again.
Yep, so basically, if you read through this, that's exactly what it says. It says we will clear this pin when we count to our number, and when we reach the bottom of the count, so this is for, I guess,
When we overflow.
when we overflow, then we'll set it, so we'll make it high. And this does the opposite. We'll set it high when we count to our number, and we'll clear it when we reset our counter. So basically, you just pick the one that matches what you're trying to do.
And if you want, if you want it to always be on, you would just set your output compare register to the top value, so to 255. Okay. All right, so we want to know how fast we want our pulse width modulated signal to go. So we need to set our prescaler accurately to do that. So let's say we wanted to, keeping in mind that our counter counts from 0 to 256. So whatever frequency it is going to be the system clock, 8 megahertz again in your case. We divide that by 256 times whatever prescaler we set. So like I said before, when I used the example of 8, 8 megahertz turns into a 1 megahertz clock. So it's counting the counter at 1 megahertz. And then the actual period or the actual frequency of the signal is going to be that divided by how high the counter is counting. So in this case, that's 256. So we divide by that, and that's our clock frequency.
So a couple of interesting things to note are here. First of all, you can see if you wanted to have an external clock source, so something like a button or another clock, then you can connect it and configure these external clock sources.
And you can decide whether it clocks it when the signal goes from high to low, or if it clocks from low to high.
Yeah, and the other part is timers don't really have an on-off switch, but what they do have is putting no clock source, which effectively turns them off. So if you're done using your timer or you don't want it to run for some reason, basically the way that you do that is by setting its clock to be none. And then it doesn't count, doesn't do anything, but that's basically as off as it gets.
Okay. A few last steps that you need to do in order to make your PWM signal appear. You actually have to set output compare register A or B or whichever one you're using. So, you'd have like a set motor speed function, for example, and maybe you'd pass that an 8-bit integer or something. And basically you would have to say OCR 0A equals that integer, and then it would update it. So if you set it to 128, that would be 50% PWM, because 128 divided by 256 is 50%. So if you set it to 0, it would turn it off. Set it to 255, it's on all the time, that kind of thing. So you actually need to set those values. Probably you want to set them multiple times in your program because you're probably varying the speed of your motor or whatever. And very crucially, but simple, but obvious, but also easy to forget, is the pin direction actually has to be set to an output. You don't have to turn the pin on, but you do have to make it an output. So that's the DDR, the data direction register, from way back 2 weeks ago. You have to set it to be an output. Okay, so configuring a buzzer. So
This is from the data sheet.
this is from, yeah, so let's just parse this a little bit. We can make a frequency that has a 50% duty cycle, so we're not changing the
How much it's on or off.
yep. And we use fast PWM mode, so you already know how to do that. But instead of using the kind where we set the counter to count all the way to 0xFF, instead we have it count to the output compare register A. That's the other fast PWM option. And we'll set it to toggle its logical level on each compare match. So that means COM 0x10 is equal to 1. So the waveform generated can have a maximum frequency. It can go really fast. It can go up to the clock I/O divided by 2. So if you set your prescaler to no prescaler, just divide by 1 at 8 megahertz, you can make a 4 megahertz signal this way, because essentially you're going to count to 1 and change it, and then count back to 0 and change it again. So it toggles every time it hits that. So it says it's very similar to the output compare A toggle in CTC mode, which is exactly why don't use CTC mode anymore. So again, you would use this specific fast PWM setting, and then you would use this. So notice, like, this port description, it's kind of saying if you set these bits to this, then you still have to worry about how you set WGM02, but if you set that to 1, which we're doing, then it's going to toggle whenever we match, whenever we have a compare match. So that's how you do buzzers, basically. That's your setup for a buzzer. And then again, you need to set your output compare register. You need to set this value and change it in order to generate different frequencies. If that's confusing right now and you have a buzzer on Gadget 1, we can work on it a little more. Because you won't be doing that as any of the homework assignments. Yeah. Okay, so just a note on timer 1, we've been talking mostly about, like, all of the settings I've pulled are from timer 0. Timer 1 is just section 12, timer 0 is section 11. The operation is pretty similar, but there's some subtly different register settings because you have more options. You can make 8-bit PWM, 9-bit PWM, 10-bit PWM. So you just have a few more options. And you can count, instead of counting just 255, you can count to 65,530. All right, so yeah. And we'll not talk about software PWM today.
Yes, next software PWM. So basically, we have a thing that generates this interrupts. Now let's use it to do stuff. And sleep mode, which is kind of similar, which is we have a timer that's used to turn on and off our device over a long period of time.
And the next assignment is actually use the button to enter and exit sleep mode, basically turn it into a power button, and then increase the LED's awesomeness through software PWM by making it color fade and all that stuff. So that'll be assigned on Wednesday. So next lecture we've covered, I guess, the basics now. The next lecture will tell you, hopefully, how to do the next programming assignment, essentially, to some extent. Any questions about the lecture or anything else in class? Hope that wasn't too
Still.
deadly. Okay.
All right.
See you guys. Come up.